cells, as well as photoelectrochemical water splitting, various nanomaterials, synthetically how you get there, what they look like, also some inorganic sensitizers, particularly via ALD for dye cells. And today, I'm really glad that I chose to orient my topics this way because we've had such a great introduction over the last 2 days about quantum dots for nanocrystal PV. Focus of my research is primarily group 4 nanocrystals, so silicon, germanium, some alloys as well, but also some 3,5s. But today I'll be focused on the group 4s and what the community is doing there. First, I want to step back a little bit and do something that you may get in the 4 to 5 p.m. Time slot. I don't know if most people are presenting these types of data, but when you look at our portfolio of renewable energy options, we really have hydro, geothermal, wind, nuclear, biomass, and solar. That's basically it. And one could argue even the nuclear shouldn't be here, but these are sort of the carbon-free sources that we all think about. And so if you look about the third row here, you can see that the economically feasible potential, that's the potential terawatts of energy that can be converted. You can see here that they're very, very small numbers. And solar is really the only one that has a large number. Compare that with 90 terawatts worldwide annually for photosynthesis. We really need about 20 new terawatts of energy in the near future, the next 20, 30 years, if it's going to be all renewable in order to flatten off the amount of CO2 that we're currently producing and have in our atmosphere. And so if you think about that, that's covering 16% of the globe, or 8 times 10 to the 11 meters squared of area. And so that kind of looks like this if you look at the US. And so it's a very, very large area, and I always like to compare it to the amount of paved roads in this country, which is 0.6% of the US. And so just think about all of the effort that's taken to go into making our highway systems and all the other local roads we have. Well, we have to do that by an order of magnitude more in 10% solar farms to get to 20 terawatts of energy. Now, if we want to be selfish and just be the US here and produce our own energy, not for the world, then that's a 3 terawatt box, which is about what the US uses every year. And so, again, it's a huge problem. And you can map these boxes out worldwide, and you can see that, well, Europe, sorry, for everyone from Europe, you don't get enough sun. So it's got to be somewhere near the equator, and that's sort of what it looks like. So when you back it up to the scale of the world, it doesn't look quite as daunting, but it is still a massive effort. So here's your first clicker question of the day here. U.S. electrical production. This is natural gas over here, nuclear, hydroelectric, coal is down at the bottom, and this is where we currently get our electric power production, at least in $2,009, and that's sold to the grid at a wholesale price of 5.7 cents kilowatt hour. And so back in 2010, when these data were collected, solar was about 15 cents a kilowatt hour, and I'm just curious to see if what you guys think, at least in 2010 dollars, or even just guess right now what the lowest cost of all these 5 technologies are for new installations. So there are your answers, and the overwhelming majority of you are picking the correct one there, which is natural gas. And those of you who live in the western part of the U.S. here, the western part of the U.S. know very well that the fracking technology that the oil and gas industry has developed has been a huge boon into getting more natural gas sources. It's very clean, and that's the difference between coal and natural gas, is that coal requires lots of scrubbing technologies to get out the NOx, the SOx, and the mercury that's inherent with the coal. And so natural gas doesn't have nearly as many of these issues, and so installing a modern-day power plant is actually the cheapest now for natural gas. The cool thing is that wind is not far behind, and it's pretty much cost competitive. And so going forward, I only expect that that will decrease and be about the same. Okay, so I deleted a number of other slides about why we need to go into third generation technologies. I think Art Nozick and Matt Beard covered that fairly well Wednesday and Thursday. And we had a great introduction from Matt over the past 2 days about these nanostructured or nanocrystalline PV devices. And so here's a couple of reviews that you can read. And there's the first sort of certified solar cell out of NREL. And so we've also heard a ton of these fundamental questions about what we need to do to advance nanocrystal photovoltaics. And really it's to control doping, or at least the type of charge carriers in the system, and also to look at charge transport, particularly how the distance, the conductive versus insulating ligands affect things, whether we have passivated surface defects, and also to encapsulate these from oxidation. And so Matt, again, gave a great intro to that, and so we're all now very familiar with this. And the thing that I want to talk to you about today is group 4 nanoparticles. And if you're a chemist, you'd say, well, it's group 14, but the PV industry uses the 4B terminology, and so we'll just stick with that. So silicon is group 4, as well as germanium, tin, etc. And so silicon, saw this image from Wednesday from Art Nozick. This is about a 10 nanometer silicon quantum dot. And Matt Beard and other researchers at NREL showed that these types of quantum dots do exhibit multiple exciton generation. And particularly with the group 4s, we have a huge amount of modern infrastructure already existing with silicon in particular, microelectronics and PV industries. And so these could potentially interface very neatly with those industries. Another thing that we can do is look at how we can change these structures. So we can look at just the homolytic compounds, we can look at core shells or alloys of these materials and see how that changes their fundamental properties. Going from nanoparticles to rods to nanowires, another thing that we're interested in exploring. In terms of the quantum dot research, looking at how surface modification of these things will change their fundamental properties. Going to a olefinic group on the outside, you could potentially couple the wave function of the p orbitals here into the quantum dot, and if you have a conjugated ligand at the surface, that could potentially change your optical properties. And then when we assemble these into film, how do the surface groups affect the nanocrystal separation distance, inner particle charge coupling, and we've gotten some great tutorials earlier this morning on those things. So now I want to jump right into how one makes group 4 nanocrystals. There's a number of different routes that have been published about how one makes them, and unfortunately most of them get it wrong. For instance, this one here, we can take germanium tetrachloride, or you can use silicon tetrachloride as well in a micellular structure, and reduce that with lithium aluminum hydride, and you supposedly get these germanium nanocrystals. If you do this reaction rigorously air-free in the absence of oxygen and water, you only evolve germane gas or germanes, and so you need some sort of oxygenation in order to nucleate your particle. And so that's one of the things that I found in the course of my research. There's also some other preps that do work out there, such as this one here, where you take a germanium-2 complex, and this will be very similar actually to some of the chemistry that I'll be talking about in a little bit that we've developed at NREL. So you can see this is germanium diamide here. You reduce this at 300 degrees and you get your germanium nanoparticle. We also can use silicon tetrachloride and zintyl precursors. This is this magnesium germicide here, and you eliminate magnesium chloride, and you can form actually core shell structures in this case. And so when I entered the field about 2009, a publication from Victor Klimov's group at Los Alamos had just been published showing that you can take germanium-2 iodide and reduce that with butyllithium in amine solvents in the presence of octadecene to get your germanium octadecyl cap particle. And I'm sure you're all familiar with how nanoparticles are made in this hot injection technique. Basically, you dissolve the germanium diiodide in your amine solvent, and and then you quickly shoot in your reductant, in this case Bewley. It's very similar to the quantum dot technique where you have a hot solution and you inject in your precursors and you get that quick burst of nucleation. It's exactly what happens here. But in the metal chalcogenide syntheses, what often happens is you can actually control the size. You can adjust the time or temperature or the concentration to control your size of your nanocrystals, and that does not work here. And so that really perplexed the Los Alamos group. And so what we did at NREL was we thought about this for a while, and in our exploration tried adding a germanium-4 precursor, and that germanium-4 precursor was able to control the size depending on our ratio of our germanium-2 to germanium-4 between 10 and 11 nanometers. And we rationalized this by the different reduction potentials of these two elements. Germanium-2 has a higher reduction potential, germanium-4 lower reduction potential, so there's less driving force for the germanium-4, and therefore leads to a more controlled reaction. And so the ratio of the germanium-4 again to germanium-2 we're able to control that, and you can see for a 1-to-1 mixture of the two, we get about 5 nanometer particles. And that's sort of the standard one that I'll be talking about today. Most of our crystals appeared to be single crystalline. It's tough to see in this image here, but we did observe some that are partially crystalline or are twinned, somewhat polycrystalline. So you can look at the absorption profiles of these and the raw data on the left. The Taos plots are on the right, where you can see here these are the smallest nanocrystals, 2 nanometers, and we can, for the smallest nanocrystals, control the band gap all the way up to 1.6 eV. The bulk germanium is 0.67 EV, and for our largest nanocrystals, 11 nanometers, we're basically at bulk. And so that fits very well with what we'd expect from quantum confined germanium nanocrystals. And so we thought a lot about the formation mechanism and how this differs from the germanium-2 only case, as well as some of the typical metal chalcogenide syntheses. And we did a number of investigations and have concluded that there's a pre-equilibrium that occurs at some point lower in the reaction, about 220 degrees, where we get disproportionation of germanium-2 into these seeds and germanium-4. And then the germanium-4 at higher temperatures leads to further growth of the nanocrystals. And so this fits exactly with changing the ratio, giving larger particles. And so if we have a smaller amount of this and a larger amount of that, then we can change our particles on the other side, which basically changes all the equilibrium. And so you'll notice here we have this octadecyl group on the surface here. It comes from octadecene over here. And so a little bit of terminology for those of you who are chemists in the audience. How do those groups get on there? There's 4 choices here: octadecylation, hydrogermylation, germination, hydrogenation, or magacination. Magic. Oops, sorry, let me hit play here. There we go, vote again. Popular there. Okay. Got 34 votes now, and I'd say that dehydrogenation was the one that most of you picked. And hydrogenation, which is something I'm sure you've all heard of, is taking a molecule of hydrogen and adding that across a double bond. So that's close, but not quite. What we're actually doing is hydrogermylation. We're adding a germanium hydrogen bond across a double bond and forming our germanium carbon bond there. And so we have a fully saturated species. Hydrosilylation is something that is well known in the chemical literature. It's been used for a long, long time to passivate silicon photovoltaic structures. And so this is the analog of hydrosilylation. It's called hydrogermylation. Okay, so moving on here, the photoluminescence of these germanium nanocrystals matched very well with their band gap. And so you can see here we have slightly lower energy emission than their band gaps. And so that's represented in the spoke shift that Mark introduced really great, much better than I can do earlier. And so that fit very well. You'll notice also that I only have the smallest particle sizes here. We did not observe emission from our 6 and 11 nanometer samples. That's something that we're still looking into, but in the end, we think that there's probably some amorphous material, particularly as you grow the particles larger, that is limiting our ability to see emission from those. And so another question that came from the literature, in the germanium nanocrystal literature, there's maybe 40 or 50 papers out there, and all but 2 have shown this blue or UV emission located around 400 nanometers. And so we were very perplexed with that. The Klimov paper showed that there was IR emission, and there was one other paper from the late 90s, a physically deposition method, where you have germanium nanocrystals embedded in an oxide matrix, and that also showed an IR emission, which is what you would expect if it were true bandgap emission. But there were all these papers out there showing that it wasn't, and that you could actually change your excitation wavelength and get a different emission wavelength. And so what we did is we tried 2 different wavelengths for excitation, 405 and 750 nanometers, and as one would expect, you can emit, or you can absorb different wavelengths, and via these vibrational relaxation, that Mark was just described, that would get you down to a lowest energy state, and then you emit into your, back into your valence band. And so this was really good confirmation that we're observing this band edge emission here. And so you can read all about this in a paper that we published recently. The thing that we took from this and have done in the recent past is that we noticed that we could add 2 different types of main group element halides into our reaction and get germanium nanocrystals. And we thought, well, what about other main group element halides? Can we add those in to dope these particles? And we've now shown that we can do that. The key is having a reduction potential of your main group element that's very similar to that of your germanium. And so if you use germanium iodides, you want to use many of these main group element iodides, which we've done. And so that allows us to make all those particles that I've showed there, typically in the order of 1 atom percent doping, although we've gone up to 3 to 5% doping. Once you get into the 10% doping level, you start to get some formation of the metallic element rather than a true doping. And so the absorbent properties and photoluminescent properties don't change significantly. The only case was the arsenic one completely quenched the emission, which we're not exactly sure why. But there are some slight size differences, which is why these things shift around a little bit. But for us, the main issue was convincing ourselves and potential reviewers of a paper how, or if the dopant was actually in the particle, or if it was simply part of the bulk sample. And so this is something that is very, very challenging to do, because if you're looking at one quantum dot, how do you sort of figure that out versus doing a bulk analysis? And all of our typical analyses are bulk. If you remember the XRD spectrum that I showed long ago, it was so broad that you can't see minute shifts, which one would expect from typical doping, where you're seeing slight changes in the lattice constants. So what we chose was EDS, energy dispersive spectroscopy, which you can do in a TEM environment. And for the heavier elements, which are going to be much more active towards scattering X-rays, you can see here that we have little peaks for our antimony and indium. And so for us, and this is actually when we focused the beam right on a single particle, that was great confirmation that we do have our element physically within the nanoparticle. And so when one goes forward and tries to take what we've made and convert them into an electrically conductive film, the octodecimal group that we've put on there is not going to do it. It's about 2 nanometers long of grease sitting on the outside of your particle. We've talked a lot about, previous speakers have talked a lot about displacing these long organic chains, and there's been a lot of great work in doing that. The problem with the group 4 systems is that the germanium carbon or silicon carbon bond is kinetically inert, and so you cannot simply displace that with another ligand. The reason we have the octadecyl group in there in the first place is because our reactions are done at 200 or 300, and if you were to use a short chain alkene like octene or butene, something like that, that'll simply boil out of your solution. So you need to start with something that's higher boiling point, and that's why we're stuck with the octadecyl group. And so one of the things that we thought about doing was taking some inspiration from this paper here, where you can use a ligand that is thermally cleavable. And so if you're able to put a ligand on that is long chain and thus higher boiling, you can potentially either photolytically or thermally cleave that. And in this case, the terpbutyl group comes off as isobutene, and you eliminate the CO2 from right there to form a much shorter chain. So that's one approach to do that. We didn't actually have much success with our particles with this, and so what we ended up doing is simply leaving out the octadecyl and seeing if that works. And in fact, it does work. What you get are allylamine capped germanium nanoparticles. And I draw this as a date of interaction here, but undoubtedly one of these protons is also gone in some cases, and you have a germanium nitrogen covalent bond as well. And so after much trial and error, we have discovered that this type of group here is labile and allows for further ligand exchange. And so these circles here are supposed to represent the amines, the NH2 head group, and the tail is, for instance, our allyl group here. We've used polyethylene imine as our polymer for ligand exchange, and we tried all sorts of amines. We tried hexylamine, octylamine, hydrazine, on down the list of the typical things one would do. None of them displace the allylamine. This is the only one that we found to displace allylamine, and we're still not exactly sure why, but this is also the only one that seems to promote solubility in different solvents. So these things are typically soluble in aliphatic solvents. We can now take them up into more polar solvents, and so that sort of exchange from one solvent to the other, we think, is also helping out in this. And so you'll note here that the allylamine group, that's a C18 group, polyethylene imine, so this is just an ethylene group, or a C2H4 in between your amine groups here, and so it's basically a much shorter chain. It's kind of like putting ethylene diamine in between your molecule, except it's in a polymer. And so, as the picture shows here, we believe that these bring the particles much closer together. And that's actually allowed us to show for the first time film conductivity. Nobody before has been able, with these germanium nanocrystals, to show any sort of conductivity in films, and we were stymied for a long, long time until we hit on this unique surface chemistry. We did previously, with our octadecyl group chains, show that we have emission from our germanium nanocrystal films, and so that was a really great result for us because it suggests that the solution-based photophysics are also going on in the solid state, and so we're hoping that those all translate relatively similarly. And so here you can just see the current voltage curve. We did this in not in a gated system. These are just 2 electrodes, 50 micron spacing. And when we did apply a gate, we saw no difference here. And so one can see here that going from the germanium only, which is the black here, to the indium, to the phosphorus, to the antimony, we get significant enhancements in our conductivity based on what the dopant is. So again, these are all the 1% doped samples. So we simply spin-coated this germanium nanocrystal PEI film in chloroform onto this electrode, and then did the IV curves in the dark and showed about a 6-fold enhancement for the antimony doped sample. And so I also want to talk a little bit about some other methods to making group 4 nanoparticles. That sort of wraps up the colloidal routes. Many of the things that have been done, as I showed with germanium, can also be done with silicon. We've tried a little bit towards silicon, but the germanium system was working, and so that's the one we focused on. There are a number of other routes to do this group 4 nanoparticle synthesis, and one of them is developed by Jonathan Vino, and this group has shown that you can take all sorts of silicon oxide type species, polymers, silicious etc., and heat these in a reducing environment, so typically 1100 degrees Celsius with about 5% hydrogen mixture. And what that results in, as you can see here, we have an oxygen 1.5 relative to your silicon. That plus the hydrogen results in the nanocrystals effectively precipitating out. The driving force is forming that really thermodynamically stable SiO2 that for people like me is the bane of my existence in many cases because we're trying to avoid SiO2 formation. But in this case it's valuable because you precipitate out different silicon nanocrystals, and then you can take these and etch them with HF, and I'll get to that in a little bit. So Mark also referred to that magic machine that's going to produce perfect quantum dots of silicon. And, well, I'm hoping this is it. This was developed by Uwe Kortschagen at the University of Minnesota, and his group has developed this RF-enhanced plasma reactor. And so this is a system where you take silane and you pass that through an RF plasma, and that basically blows up your silicon into silicon atoms and hydrogen atoms. And when they come out the other side, they condense and form your silicon quantum dots that are passivated with hydrogen. And so this is a system that I've been building here at NREL for quite a while. We have a linear transfer arm with a load lock so that we can collect our samples very air-free, pump them into our glove box, which is right behind here, and do lots of chemistry at the surface under rigorously air-free conditions. So this is a plasma that I actually struck for the first time about a month ago, so we're getting there. Got a little strange thing here. Okay, so as I said, you can take silane gas and make silicon hydroterminated particles in this RF plasma. You can also take silicon nanocrystals embedded in silica and dissolve out that silica with HF, and those both get you these SiH terminated particles. Or you can take silicon tetrachloride, germanium tetrachloride, and make chloride capped versions also via the RF plasma reactor. So there's a couple of different surface chemistries that you can achieve natively out of the right out of that reactor, or even via this bulk technique. And so the surface chemistry of quantum dots, as we all know, is extremely important, and this is one of the areas that I'll be focused on significantly over the next couple of years. I've already shown that one can do traditional organometallic reactions at the surface, such as just a simple salt metathesis reaction, where you take methyl lithium and add that to a silicon chlorine bond, you eliminate lithium chloride and get your silicon methyl groups. I will say that this reaction is very messy. I write one chlorine here and one hydrogen atom here. That's obviously not the case. We have many, many different types of groups at the surface. There are silicon monohydrides, dihydrides, and trihydrides. You can see these all by FTIR, and there's also going to be different types of those depending on what their nearest neighbors are. You can also do this with some longer chains like butyl groups, octyl groups, be either the lithium or magnesium salts here, and do that with germanium nanocrystals. And I've done those reactions as well. Going forward with the silicon hydride capped particles, so I've talked to you about hydrogermylation, hydrosilylation already, and this is and those are typically done at about 150 degrees, 200 degrees in a high boiling solvent, and so again, you're limited by what temperature you can do that reaction at. And so if you can use a catalyst, here the most generic ugly catalyst, platinum bracket, one can do hydrosilylation reactions at low temperatures to get various different surface chemistries on your silicon nanoparticles. And so we're hoping that not only will we be able to modify the photophysics to some degree, but also leave us with functional groups such as this alkene here that will allow us to couple these things into films. And you can imagine just shining light on this. If you take an alkene and you shine light on it, what happens? It polymerizes. So that's how you make rubber and all these other things. And so we can basically just take this, throw it down, possibly polymerize it, and make silicon dots encapsulated in plastic. And so that's one of the things that we'll be looking at doing down the road. So there's some other work that's been done on Group 4 nanocrystal size purification. Primarily this has been done by Jeff Ozen's group at Toronto. And recently he's shown that ultracentrifugation achieves some degree of size selection. And these are decyl cap silicon nanocrystals made via the Vino method of the silica in silicon nanoparticles in silica, and the HF etch, and then they do this hydrosilylation to put the decyl groups on there. And so you have these C10 groups on the outside. And then with that, if you're not familiar with ultracentrifugation, I'm sure Jeff Blackburn sitting back there will be getting to it this afternoon, so stay tuned. I won't go into the details, but that's the main method for purifying carbon nanotubes, separating metallic and these semiconductor varieties. And so you can see here that the Ozen group has been able to prepare a whole wide swath of different emission intensities for these silicon nanocrystals. And so this has been a huge advancement. So final question here, as you're all starting to wonder where your lunch is coming from. I want you to look at these data a little bit here. This is sort of a similar question to what I proposed Wednesday. Look at the data. Is the data actually telling you the right answer or not? So there's a little hint. On the far left is a solid red line here. It's the far left spectrum. And then you can see this dashed orange line here. Which of those, let me start the chart here. Which of those do you all think has the comes from the most monodispersed sample? Is it the red line, the orange line, dashed orange line? Or they're probably about the same. And how would we know them? All right, so we've got about 40 answers here. Let's see what the tally is. So it's about most of you think it's the red lines, some think the orange line, and some think C. Well, I'll stop there before people get crazy. All right, so let's talk about this answer a little bit and why that is. So when I think about what makes a sample polydispersed, there's two things you can think about. The physical size, and typically we do that by transmission electron microscopy and doing a histogram. You have your lowly graduate student with a ruler on a piece of paper or some computer program measuring particles, and you get some histogram of 150 or 200 particles, and then you get some size distribution. Yes, I've done that. It's not that fun, but these are the things one needs to do sometimes. So, or you can actually look at what the physical properties are, and in this case, the optical properties, the emission. And so if you look at the free width half max, this is of this spectrum, you can see that for the red line we're about 570 nanometers, and for the other side here we're about, say, 660. And so that gets us a free width half max of 0.29 eV. And so you can convert that based on the peak max to a band gap, or at least an emission intensity of this value here. So they've got about a 14% polydispersity based on their emission line. And this is actually not too far off from what we observe via TEM. So our germanium particles, for instance, have 20% polydispersity. When you're looking for the perfect particles that Matt was talking about, you're looking for 0, right? Or more typically for the metal chalcogenides, the chemistry is advanced enough to where you can get 5% polydispersity, and that's really good. And so when we're talking about 15 to 20, we're even less ideal. And so that's going to just make Mark tear his hair out about his calculations because of our non-idealities. So let's look at the dashed orange line. Way over here, it looks much broader. Well, it is, except that we're on a nanometer scale, not an EV scale. And so that's the trick, is that even though our we have say 125, well, I guess they're about the same, but with one of the others, it worked out a little bit better that I just did the simple math on. But basically, they're about the same in terms of polydispersity. Oh yeah, that's right. Even though their free width at half max is significantly different. That comes from the nanometer to energy EV conversion. So, okay. So, lastly, I just want to talk a little bit about what people are doing with these group 4 nanocrystals, in particular what devices they're making. Recently there have been some examples of this. There have been some 5 nanometer and 3 nanometer silicon nanocrystal OLEDs that have been made by Uwe Kortschagen, who was the inventor of that magic reactor that I was showing you earlier. Jeff Ozen's group has also made a similar arrangement. And basically these are all multi-layer films where you take PDOT and you have your thin layer of silicon nanocrystals, and then you have some back contact as well. And so you can see here that they're all using these pretty insulated quantum dots for this. And not surprisingly, they're getting things that are 0.7% quantum yield. So in this case, it's red emission for these 2 nanometer dots from the ozone group. And so that's the peak emission wavelength in their case, somewhere on the order of 675 nanometers. If you look over here, the quantum efficiency for the Kortschagen group, they're almost up to 10%. But if you go down, you can see they're in the microamp per square centimeter range, and so that's not going to get you very far. If you look at more technologically reasonable milliamp ranges, 1 to 10, you're in the 0.1 range, so not too far off from what the ozone group had. There are also some silicon nanocrystal PV out there that's recently come about. The first generation was sort of making a PDOT, PSS, typical OPV structure where you have the P3HT and then silicon nanocrystals in it. Very similar to what Mark was just talking about with his calculations. So we would be doing calculations about what's going on with energy transfer within that photoactive matrix. And so in this case, they got about 1% power conversion efficiency from this actual device. I've talked to Uwe and some of his students. This is pretty much where they're stuck. And so the question remains, is this really the way, or do we want to go to a structure where we have an actual silicon or group 4 nanocrystal layer versus a more bulk heterojunction similar to the OPV or dicell systems? And so these are some questions that we're going to be exploring down the road. I'll also note that there's been a recent report on this is a single wall carbon nanotube silicon nanocrystal layer, again abutted with PDOT PSS. And so what's actually going on in these systems I don't think is very well explained. Oh, the other thing I'll just quickly mention is that these, I put naked down here, these supposedly don't have any ligands on them. In this case, they took either phosphorus or boron, so N or P doped silicon wafers, and they mechanically beat them up and made really, really fine powder based on their mechanical dispersion of this the wafers, and so that they used that then for their active layer. So that's pretty much the state of the field, and I think that the thing that's going to come out from all of this is that we really need to step back and figure out what's going on in terms of making these dots well, i.e. few defects, how to tune their surface chemistry so that when we're putting things in devices, we're not putting them with these huge insulating ligands on the surface, so that we have some control of the group 4 nanoparticle chemistry, which is, I hope I've convinced you, is much more challenging than it is for the nanoparticle systems because of that kinetic inertness of your group 4 to ligand bond. And so we've shown in our group that we can have size and bandgap control of our germanium nanocrystals, and that we can extend this to a whole range of dope samples, and that hopefully new methods are coming about, and I've shown you some that will allow us to speed the advancements in group 4 nanocrystals for 3rd generation PV. So thanks very much. Any questions? Questions? Okay, yeah.
So for your germanium nanocrystals, have you considered compound termination of those? Do you do that?
We have done a little bit of work in there, but it hasn't been successful. We've tried long chain thiols, for instance, putting those in the mix, and that has not worked.
Any thoughts about, is that a prospect dim for doing that, or are there any reasons why you?
We haven't tried exchanging that oleolamine capped with the thiols, and so that's probably something we should do. It should work. If chemistry as I've written it there is approximately the same. So, yeah, it's a good suggestion.
Yes.
Thank you. In the case of that germanium nuclei which you added in the solution as a nuclei, I want to know, is there any crystalline mismatch between the core and the germanium shell which is produced on these nuclei, or there is no crystallinity problem? And also, would you please comment how, whether is there any problem with these hot injection method on the crystallinity or not?
There absolutely is, and this is why I'm going to the magic machine and away from the colloidal routes for the group 4s. The crystallization temperature of silicon is 1100 C, and from germanium it's 800 C. So the fact that we can actually get lattice fringes and particles at 300 C in solution is amazing. I think this is why the silicon didn't work as well, is that we're just getting incomplete crystallization. So in particular, we are getting nucleation and some growth of crystalline particles, but in the end, we do believe that as one increases that growth through the addition of the germanium-4 and that mechanism, that we are growing some amorphous material on the surface, and that's what's limiting our emission intensity, which is very, very low.
Okay, yes.
You're limited on what solvents you can use because of their boiling points, and I forget the scientific word, but couldn't you use like a pressure cooker to get higher temperatures but not have it boil off?
Yeah, that's certainly something that one could try. We haven't done that. I'd have to do the math on whether the par bomb could withstand it. EHS would make me do that, so yeah. But that's a really good suggestion.
Yes.
Talked a little about the other day about making alloys with germanium silicon in a plasma reactor. And should I naively picture you putting silane and germanium and just kind of...
That's actually been done. Uwe Kortjagen has shown that that's possible. And so that's exactly what we're going to be doing.
Okay, any other questions? All right, if not, let's thank Nate once again.